Okay, starting chapter 15, which is technically titled Random Variables. That doesn't sound very exciting. I like to call it Why Not to Gamble 101, because this is the chapter in which you learn why you're not supposed to win at those lottery games, why you're not supposed to win at the casinos, save your money, invest in gold or real estate instead. So we're going to learn about gaming, and I'm not going to teach you to count cards. That is not the goal. The goal is to teach you why it's not in your best interest to throw your money away on gaming, because you're not supposed to win, and look at the number crunching behind why that casino or that lottery makes a profit. So normally we would start with just playing a game. Of course, I'm not there to run the game, so we'll just talk about it instead. We'll do plenty of card dealing and dice throwing and other things in the near future. But for now, we'll just start with a pseudo discussion, since I'm not really there to discuss with you. So I'm going to propose a game. It's a card game. You use a standard deck of cards, and every time you play, you have to pay $5. So you lay down a $5 bill, you get to play the game. So the game is, you take a shuffled deck of cards and you choose one card from the deck. That's it. You pick a card. Pay $5, pick a card. If you draw the ace of hearts, I give you $100, which means technically you've made $95 because you had to pay $5 to play. If when you pick that card it's any other ace, you get $10, which means technically you've made $5 because you had to pay $5 to play. So you still profited. If you get any other heart other than the ace of hearts, you win $5, which means you get your money back and you're back to zero. You've not lost anything, but you haven't won anything. You break even. Any other card on the deck, you lose your $5. So you're in the hole. Would you play? And under what circumstances? So, and one of the ways you could answer the question of is it worth playing is to actually play it. So you get a deck of cards, you riffle shuffle 7 times, draw a card, keep track of how much you win or lose. And then you shuffle 7 times again, you play again, keep track of how much you lose, and you tally it up as you go. And in the past, when we played this game, what happens is you might get lucky enough to win the big time early on, and then you can lose several more times and still have some money left. Or we've also seen circumstances in the classroom where we've played a few times and somebody who really loves to play and doesn't like to give up is very much in the hole, lots of dollars before they ever decide to give up. So would you play and under what circumstances really depends on how much you stand to play or stand to win or lose in the long run. Any one play you could lose money. Any one play you could win money. It's really what happens over the long term that matters. So if we played it a few times, what you would find is in just a few plays you would probably be in the hole, because there's only one ace of hearts in the deck. And the majority of the cards in the deck are losing cards. So you would lose money faster than you would make money. So you might play, and then as soon as you're in the positive, you quit. So your circumstances may be, well, when I'm in the positive, I quit. Well, except that sometimes, especially if you lose in the beginning, if you have bad cards to start with and you start off in the hole, sometimes you never can get out of the hole. So you might get lucky enough to win big in the first couple of plays and decide to quit. So that might be your circumstances. And then if the ace of hearts were worth $200, would that change your decision to play or not? If the ace of hearts was worth $500, would you choose to play or not? And once you start upping the profit of that one card, then you could stand to lose lots of times and still come out in the positive in the very long run if you play long enough, if you make that ace of hearts worth more. But you might spend a lot of time, if you have an ace of hearts worth $500, you might spend a lot of time worrying in the negative before you actually make enough money to get back out of the hole, if your luck is running in such a way that you don't draw that ace of hearts early on. So what we want to really do is look at these kinds of games from the perspective of how much do you stand to lose or win in the long run if you play, and why is this a good game if you own the casino, but it's not such a good game if you're the person laying your money down to play. That's where we really want to go with it. So that means we have to be able to do some computations. And to do the computations, we have to understand something called a random variable. Now, we've been studying variables for a really long time. We introduced to you many years ago, x is a variable. It can be 2 in this problem, it could be 5 in this problem, it could be 22 in that problem, it could be negative 15 in this problem, so it varies. Random variables in the world of statistics, they still vary, but they're a bit more complicated than what we have in algebra. In algebra, in any one particular problem, a random variable, a variable, typically has one value in a particular equation. Sometimes you can have a quadratic equation where a variable could take on 2 values that are meaningful or that are solutions. But in statistics world, variables can take on lots of different variables, lots of different values. Okay, so let's just start with some gobbledygook definitions and notation, and then we'll just have to weed through applying that notation a little at a time until we get used to it. So random variable is a variable whose value is based on the outcome of a random event. So a random variable may be which card you pull from a deck. So it could have 52 different values. A variable that is a card from a standard deck could have 52 different total values. It could be the ace of spades, it could be the 2 of diamonds, so 52 different possible outcomes. And the outcome depends on what you pull randomly out of the deck after it's been shuffled. The notation is a capital letter. So unlike algebra, where we normally use lowercase letters, we use capital letters. It's usually an X, but it can be any letter. If your random variable is the outcome of pulling a card from the deck, you might use a C for card. So you may use the letter that corresponds to the meaning of the variable. 2 types of a random variable that we're going to study in this course, and we're mostly going to be concerned with the discrete ones for the first part of this chapter, are the discrete and continuous random variables. Discrete means that you can list all of your outcomes. So a discrete random variable might be the result of pulling a card from a deck. There's 52 different cards in the deck that you could list. A discrete random variable also could be the result of rolling 1 die. And there are 6 different outcomes. You could roll a 1, a 2, a 3, a 4, a 5, or a 6. So if you can list your outcomes individually, you have a discrete random variable. Continuous random variables are outcomes that span a range of values and you can't list them. For example, if your random variable is the weight of a baby elephant, it could be lots of different things. It could be 200 pounds, it could be 322 pounds, it could be 576 pounds, it could be 422.7 pounds. So there's sort of a minimum weight that a baby elephant could be. There's probably a maximum weight that a baby elephant can be. And anything in between those is possible, and you can't list those. So it's like values on a number line. There's no gaps, there's no holes. Anything from a lower bound to an upper bound is possible. And so we will be mostly concerned right now with discrete random variables. And that's what we're looking at in the card game. You could get an ace of hearts. You could get another ace. You can get another heart. You can get another card. So there's 4 different values that you're concerned with. Those are listable outcomes. So that's a discrete variable. All right, more gobbledygook vocabulary and notation, which is just the stuff we got to do to introduce it. So we are going to learn today how to build a probability model. So we've done 2 different models before. We've used simulation models, which were useful for determining outcomes when we couldn't buy all the boxes of cereal that we needed to see how many boxes it would take to get a picture of Serena Williams. We've seen probability models that involve how many points you might make if you get free throws late in the game. So we've seen lots of simulation models in the past. We've seen the normal model, which is a continuous model. So this is the third in all the models that we study. The probability model is typically a table that lists a bunch of outcomes. And you only use a table for a discrete random variable. If you have a continuous variable, your probability model is probably going to be something like a normal curve. For a discrete variable, you want to list your outcomes. So your model is going to be a collection of all the possible values and probabilities that they can occur. It's going to come in the form of a table. It's going to include the outcomes in the sample space, all the things that could happen. The possible values are labeled, usually lowercase x's, sometimes with a subscript, and then the random variable itself is the capital letter, and then the table also lists the probabilities of each possible value of x. Now here's where things get a little bit tricky. Capital letters versus lowercase letters, they mean different things. So let me deal with that first right here. So the name, let's add some info here. Name of the variable is a capital letter. So I might say, for example, let x be the result of rolling a die. So it's like it's what we call the variable. It describes what the umbrella under which all the possible outcomes belong. Then the possible outcomes are lowercase. So possible outcomes are lowercase letters. And I'm going to have to probably arrow down a little bit to make it fit. So little x would be the set of numbers 1, 2, hands in the way, 3, 4, 5, and 6. And notice I'm using set notation, braces separated by commas is set notation to show a discrete set of numbers. So the little x could be a 1, 2, 3, 4, 5, or a 6. And we might see in some textbooks each of those possible values having a subscript assigned to it. So like the 1 might be little x sub 1, and the 2 might be little x sub 2, and the 3 might be little x sub 3, and so on and so forth. So you could number, it's really just a numbering device for all of those individual possible values, and so all of your possible x sub i's are this set of numbers. We don't often put the subscript in. We just say the little x's could be these values. They could be numerical values, but they could also be categorical values. They could be red ace, they could be heart, depending on what kind of variable you have. You could have quantitative or you could have categorical. So capital letters are for the name, lowercase letters are for the outcomes, and we could use subscripts for them. That's going to seem complicated until you've seen it enough to get comfortable with it, so you're just going to have to give it time. Alright, so one more bunch of crazy to look at before we actually get back to the card game and see what the model looks like for real. We will come back to this from time to time as a sort of a reference sheet. Until then, this just looks like something that's kind of crazy and kind of scary. So don't be scared because we haven't really learned this yet. Okay, every model has parameters. For example, a normal model has 2 parameters. A normal model has a mean and a standard deviation. A probability model is no different. It's going to also have parameters. Lucky for us, it also has a mean and it also has a standard deviation. So it has the same type of parameters that the normal curve does. But in this case, we're looking at a discrete model, listable outcomes. The mean is sometimes referred to as the expected value, so interchangeable terms. How much do we expect to win if we play the card game? Well, what we expect to win is the average of playing the game a lot of times. And we calculate it with a formula, and the formula can be written mu, which is the mean of x. We're going to add that out front here. It could be written the mean of x with the mu, the Greek letter, because it is a parameter for a model. We use Greek letters. Or in the case of gaming, we often call it excuse me, We also call it E of X for expected value of X. Interchangeable notation, it doesn't matter which one you use. This formula is in your blue book. This formula will be given to you on the AP exam, but you have to be able to look it up and use it when you need it. Okay, the formula says that the expected value or the mean is the sum, capital sigma is a sum, of all your possible outcomes, all of your little x's, all the values that you could, that your values of your variable could be, times the probability of all those variables. And then the notation options are shown here. So notice you can use subscripts or you could use function notation. Don't let this overwhelm you. We're going to see this in action in a few slides, and it'll make more sense then. Standard deviation has a lot of gobbledygook with it. There is no reason for us to look at this today. We will not learn to do standard deviation until I get back next week. So let's just skip over that one for now. Okay, so let's revisit the card game and actually dig into what this expected value or mean business is. Alright, so it's the same card game we mentioned before, and we're going to create a probability model for the amount of money we're going to win, which is a table. So the table really is just an organizing tool to help us get all of our information gathered up. So normally the probability model has 3 columns. Sometimes it's 2 if the first and second columns are the same thing. And sometimes they're the same thing. In this case, they will not be. So in the first column, we have our possible outcomes. And in this card game, there are 4 different possible outcomes. We could get the ace of hearts when we draw a card. So ace of hearts, I'm going to abbreviate so that it'll go a little faster. Second possible outcome is any other ace. So we'll call that other A for other ace. The third outcome is any other heart. So we'll say other heart for this one. And the last one is any other card, or let's just say anything else. We'll call it else. So those are the 4 possible outcomes for this card game. In the second column, we want to list all the values of those outcomes. So X is the amount you win, okay? Probability model for the amount of money you win, capital X. So that's the name of the variable, amount of money you win, X. Well, you could win 4 different amounts of money depending on which outcome you have. So in the second column, we're going to say the amount of money you win, capital X, let it equal all the possible little x sub i's. So what are all the little x's that big X could be? What are all the values for the money you could win that exist? You don't need the subscript there. I normally don't write it, so I'll probably not write it in the future. So it costs $5 to play. We get an ace of hearts, we win $100. Okay, if we win $100, the actual amount of money you win is technically $95 because you had to spend 5 to play. So we'll make that adjustment as we write that down. So the amount of money won equals 95 is like your X sub 1 in this case. If you get another ace, you win $10. Well, you had to pay 5 to play, so technically your profit is $5. Any other heart, you win $5, which means technically you break even, so your winnings in the long run is 0. Any other card, you lose, which means you lose your $5, so you're $5 in the hole, so that's going to be a -5. So you stand to win as much as 95 in a play or lose as little as 5. So that sounds really good because the winning is bigger than the losing, except that you've got to consider one other piece of the puzzle, and that's the probabilities of these happening. They're going to matter, and that's what goes in the third column. So in the third column, we want the probabilities, that's capital P, that the amount of money you win, capital X, is equal to each of those little x sub i's. Probability that the amount you win is equal to a particular value. So we want the probabilities of all these things happening. Okay, well, let's start with the ace of hearts. there are 52 cards in the deck. Only one of those cards is an ace of hearts. So the probability of an ace of hearts is 1 out of 52. There are 3 aces that are not hearts. So 3 out of 52 cards is the probability of another ace. Okay, hearts. There are 13 hearts in a deck, 13 cards per suit. One of them is an ace. That means the other 12 are other hearts. So 12 out of the 52 cards in the deck are other hearts. So we have a 12 out of 52 chance of getting that card, one of those cards. Now, last but not least is all the other cards in the deck. So something out of 52. Well, the easiest way to fill this one in is making sure all of your numerators add up to 52, because this has to include all the possible outcomes, which means we have to have 100% of outcomes in this sequence. All of these numbers have to add up to 1 or 100%. So let's add up what we have in our numerators so far. 12 plus 3 is 15, plus 1 is 16. We've got 16 cards accounted for here. 16 from 52 is 36. So that means 36 cards left behind are not in the first 3 groups, so they have to be all the other cards. Again, check to make sure those add up to 1. If they don't add up to 1, you're either have a miscalculation or you're missing a possible outcome. This table is the model. This table is the probability model. So if you're asked to create a probability model on the AP exam, they mean draw a table. There will be times that the outcomes and their values are the same thing, and you can get by without this second column. We'll see that at some point in time. All right, now, part 2 of this puzzle. Calculate the expected value for the money you win if you play. How much do you, on average, expect to make when you play the game? On average, in the long run. That's what we really want here. That's a mean, okay? We could either call it the mean of X, mean of the amount of money, or we could call it the expected value of X. Either notation is appropriate. E of X is probably the easiest one to start with because expected value starts with an E. E is for expected value. We have a formula for this that we saw on a previous page. The formula for expected value is the sum of all of your X values, which is all the money you could win, times the probabilities. Okay, so if we look back at our table, our first possible X value is $95, and it has a probability of 1 out of 52. We're going to multiply those together. So 95 times 1 over 52. Then we add, that's where the summation part comes in, the second product. So we take the second possible outcome, $5, and multiply by its corresponding probability, 3 out of 52. So 5 times 3 out of 52. Then we take the third possible outcome, which is win $0. That can happen 12 out of 52 of the time. Now, I know that this doesn't add to the total. So when you put this in your calculator to chunk it all out, you can leave that term out, but you don't want to leave it out when you write out the work. You have to show the work that gives you this final calculation. Then we have the last possible outcome is -5 or -5 times its corresponding probability. And I can either do plus and -5, which is just kind of messy, or I could do -5 times 36 over 52. And what we're really doing here is we're doing a weighted average. We're taking all the different possible outcomes and we're multiplying by their probabilities, which we think of as weight. It's kind of like calculating a weighted grade in a class. Your test scores multiplied by their weights, your homework scores multiplied by their weights, your quiz scores multiplied by their weights, and then you add it all up to get your final grade. It's the same process. So this is really a weighted average. Which is why we refer to it as the mean of the amount of money you win, because it's an average. Now, you've got a couple choices for how to get this in the calculator. You can type it in just the way it looks. You can leave out that third term because it's going to be a 0 and doesn't matter. Or you could multiply 95 times 1 plus 5 times 3 plus, you can leave that one out, minus 5 times 36, and then divide that total by 52, since they all have a common denominator, and crunch it out a little bit faster. And how you use your calculator to accomplish that is a personal choice. But try it out, make sure that you know how to get that in the calculator. When you're all finished, you should come up with a negative 1.35. Now remember, this is money. So this is $1.25 negative, or negative $1.35. I said 25, it's 35. Which means in the long run, you average losing $1.35 every time you play the game. It's an average. On average. If you play it a lot, this is what you average losing each time in the long run. Let's summarize that on the next slide. So what does this result mean? Well, it means that on average, this is super important, on average, it is a mean. On average, we'd expect, remember it's a model, it's a prediction, to lose $1.35 each time we play. So if you play one time, well, that doesn't really give us an average. One time's not an average. So let's do 10 times. If you play 10 times, you would average losing $1.35 per game. So you would expect, in a perfect world, to lose $13.50. If you played 100 times, you would expect to lose $135. If you played 1,000 times, you would expect to lose $1,350. And the more times you play, the more likely it is that your actual losses match this theoretical average here. Now, you got to think of it as a big picture thing. Does anyone ever actually lose $1.35 playing this game one time? No. No. In a single game, we'd win $95 or $5 or lose $5 or get nothing. So in one game, then one of those four outcomes has to happen. But the negative 135 is an average, I didn't spell that right, per game loss. It's about what happens over time if you keep playing the game. So you play the game one time, you lose some money. You play again hoping to win some money back. Or maybe you win the first time and you're feeling lucky and you keep playing, and down the line you're in the hole and you keep playing hoping that you can get back out of the hole. Well, this is telling me that in the long run I'm going to lose money. The more times I play, the more likely I am to get this $1.35 on average per play result. Okay? This is more important information for the person that owns the casino than it is for the person playing at the casino. If I own the casino, what I know is at the end of the day, if 100,000 people played this game, then I stand theoretically to win $135,000 off this game from those 100,000 people. So this is really more about what I stand to win if I own the game instead of what I lose if I play the game. But this also tells me that as a player, if I sit at the table and I play long enough, ultimately I'm going to lose. Because that's how the game is structured. It's structured for me to lose, on average, $1.35 per play. And in the long run, that's what's going to happen. In a perfect world, you'd have to play 52 times to win the $100 one time. Because only one of the 52 cards is the $100 card. So from one game to the next, anything can happen. But in the long run, you're supposed to lose. So any result, let's make it, any result is possible in a single play. It's the long run that matters, and that's what the model tells us. The model tells us about the long run. So the large numbers, what does the large numbers say about this? In the long run, we stand to lose. In the short run, anything can happen. If you play 10 times, you could win a lot of money. Well, you could win more than you lose. We'll say that. But in the long run, if you play long enough, ultimately you're going to lose money. So if you get lucky enough to win the first couple of plays, quit. Move on. Do something different. Okay, we're almost done. So we're going to look at one other example of an application of this expected value calculation. And then wrap it up for the day. So this is kind of a long one, but the computations are easy at the end of the line. So we have this man who took his truck in for repair because the air conditioner was cutting out intermittently. So it worked, not work, work, not work, work, not work. When it's hot, that's not cool. The mechanic identified the problem as dirt in a control unit. He said that in about 75% of such cases, that sounds like a probability, drawing down and recharging the coolant a couple of times cleans up the problem and costs only $60. If that fails, the control unit must be replaced at an additional cost of $100 for parts and $40 for labor. Okay, so we have costs, we have probabilities of success. Okay, define the random variable and construct the probability model. Okay. Well, let's see. Let's go on to the next slide where we actually have these divvied out with some space between them. So here we go. Define the random variable. Well, what am I trying to calculate in the end? I actually have to read on to know for sure what the random variable is. Here it is. What is the expected value of the cost of repair? That's the random variable. So what we're trying to find the mean of, that's our variable. So sometimes I have to look past that first question to get it. Usually it's in the stem of the problem. It just isn't in this one. So let C equal cost of repair. You could call it X if you want to. C for cost makes some sense to me. And construct the probability model. Okay, well that's a table. So we're going to start with outcomes, and then we'll build the table from there. So in this case, there's only two things that could happen. It could be fixed just by the drawing down and recharging the coolant. So we'll call that a recharge. And then it says if that fails, the control unit must be replaced at an additional cost. So they try the recharge and then they have to replace. So we try the recharge, it doesn't work, then we replace. Okay? So two things could happen. You could recharge it, it works, or you might have to also replace it after you try the recharge. Okay, now we want to know the cost of the repair. So cost of repair, big C, equals, what could it equal, little c? I'm going to leave the subscripts off this time. Well, the recharge costs $60. So if I only have to recharge it, it's only going to cost me $60. If I have to recharge then replace, I have to pay the $60, plus I have to pay the $100 for parts and the $40 for labor to get the replacement done. So that's another $140 added to the $60, which is a total of $200 for that repair. Then we need the probability that the cost equals each of those little possible costs, little c's. The recharge happens or fixes it in 75% of the cases. So the probability of it working is 0.75. That was up here and it's part of the problem. Which means in the rest of the cases, that's the other 25%, the replacement will fix it. Again, this last column should always add up to 100%. That's the probability model. Now we're going to do the calculation for the expected value. So on average, what does the repair cost? Okay, expected value E of X equals the amount of the repair, cost of repair, $60 is one of the possible costs, multiplied by the probability 0.75, plus weighted average, so we're going to add these together for an average, 200 for the second possible value of C, times its corresponding probability of 25. And when we crunch those numbers, we come up with 95. I'm going to go ahead and put the units on. So $95 on average to repair it. So what does this mean in context? On average, well, let's see. We never actually are going to pay $95 for a repair. We're going to either pay $60 or we're going to pay $200 in any one repair. So really, the average is more meaningful on the end of the owner of the establishment. So the mechanic is going to make, on average, $95 per repair that he does. So on average, the owner can expect to make $95 per repair. Now this is an important thing for the owner to know, because if the owner knows that over the course of 3 months, normally he'll make 1,000 of these repairs, then he'll know that in a 3-month span, he will stand to make $95,000 on these repairs. And it's looking at those long-term totals that help owners of businesses or casinos or whatever's going on decide how much to charge so that they make the profit they need to keep their business open. So this information, this average cost, that really is important to me as a consumer. My car is going to cost me $60 or $200, but the owner wants to know the big picture, and that's where this mean or this expected value is useful information to the person who's actually doing it repeatedly. Okay, so we've looked at a couple of examples now where we have a context, where we built the probability model, and we can interpret that mean or that expected value when we're done. We're going to look at one more slide and call it a day. I know it's been long, but it's a big one, and we needed to get through it all at one time. Occasionally, and in the textbook they'll give you a couple of those, you get some what I call naked problems. There's no context. You don't know what the context of the problem is. They just give you a probability table and say compute the expected value. Can you use a formula? So here's a couple of examples. So we'll call this first row that uses X is problem number 1, and this second pair of rows that uses Y is problem number 2. So you have two different random variables. You have the random variable X, and little x could be a 0, 1, or a 2, and the probabilities that correspond to those are given. Notice they add up to 100%. And then y is a second value. We know that it has the 4 values, 100, 200, 300, and 400, and its corresponding probabilities. And we want to find the expected values of each of those. So number 1, we want the expected value of the random variable x, the first one. So we take each of these outcomes, 0, and multiply by the corresponding probability, 0.2, add to the next one, outcome of 1, multiply by 0.4, its corresponding probability, plus outcome of 2, multiply by the corresponding probability of 0.4. When you crunch all of that out, you end up with a 1.2. So it's just naked number crunching, stick a number in a formula, multiply and add. We will need this result for some problems we're going to do tomorrow. So we want to make sure we have that in our notes to look back at tomorrow. Let's do the expected value of y while we're at it. So for the value of y, we could have a value of 100, and that one has a probability of 0.1. Or we could have a value of 200, which could happen 0.2 is its probability, plus 300 times 0.5, plus 400 times 0.2. And when we multiply that all out, we end up with 280. We have no context. We don't know what the units are, so we can't really interpret it. We're just practicing applying the formula. So quick and easy. You'll have a couple like that in your homework that you can just speed right through. Okay, so the day one homework is there in your notes. It's pretty quick. You should be able to fly through it with the time that's left. If you don't get finished, you got a 3-day weekend, and I'll be back on Tuesday, and we'll take questions and pick up where we left off. Have a good weekend.